Hello everyone, this is the video lecture of section 5.7 and Appendix G combined, part 2, second part. In the first part, we learned some additional integration techniques, mostly trigonometric substitution technique, a bit more advanced ones. And then we already started with partial fraction techniques, which is about integration of rational functions, where numerator has a smaller degree than that of denominator. Okay? And then toward the end of the first part, we did one example, A and B, where your denominator can be factored into two linear factors. Now we have to think about more types, different cases. For example, what if you have something like this, x minus 2 cubed, okay? If you have, degree 4, degree 2, so satisfying this form, in that case, this can be written as a over x minus 1, this one, b over x minus 2, c over x minus 2 squared, and d over x minus 2 to the third power. Instead of having only this one, you have to have all powers covered. Okay? Quite interesting. You can always have this form uniquely. Okay? So, this is the still case when you have all linear factors. The difference between this case and the previous case is that some linear factors were repeated, okay? But still everything is linear, just some repeated ones, okay? But we know that polynomials cannot always be factored into only linear terms. We are talking about real coefficient polynomial. So if you solve this equation, we know that real coefficient, then you could have some real numbers like this. That means correspondingly you have these kind of factors, right? Okay. But then we also know that you could have imaginary root, but in that case you will have complex conjugate pair. They are both coming from x minus 2 squared plus 3 squared, that factor. Because when you set this factor equals 0, you get minus 3 squared, so x minus 2 square root of negative number is the square root of this one, plus minus I, isn't it? So if you have a plus minus bi, that is coming from this. These are called irreducible quadratic. Okay? So whenever, all polynomials can be factored into either linear polynomial or irreducible quadratic polynomial. One of those two types. And irreducible quadratic polynomial can be always written this using complete completion of square, right? Of course, this can be written as x squared minus 4x plus 4, 9 plus 13. Alright? So, what happens if we have something like this? So irreducible polynomial is basically a quadratic polynomial. Quadratic polynomial with real coefficient whose zeros are imaginary. Okay? Like this. What if you have, how do we split? How do we decompose? Using partial fraction, the form is, linear one, as always. For this one, now this one has to be bx plus c. irreducible factor, quadratic factor, you have to have this. Now, what if you have over, let's say, x plus 2, let's say, x repeated linear, repeated irreducible quadratic. Then repetition twice, a over x plus 1, b over x plus 1 squared. For this one, cx plus d over x squared plus 3, dex plus f over x squared plus 3 squared, all the way to third power. Gx, EFGH over third. Now you see the pattern, right? Whenever you have some higher power, you have to include the terms of all the power, not just the highest power, but every power. And your numerator will be constant if your denominator is linear or repeated linear. From the irreducible quadratic, just linear. Cx plus d. So constant times x plus another constant. Okay? So the rest of the lecture will be about these cases. Alright? Okay, let's do example 7. Example 7. Evaluate x cubed plus 2x squared plus x over 4x plus 2 dx. I'm going to call this integral as capital I. Okay? Alright, solution. So x squared plus 4x plus 2 over x cubed plus 2x squared plus x. Again, you have to factor denominator. So that would be x squared plus 4x plus 2. Factor out x squared plus 2x plus 1. Right? Which is in turn x times x plus 1 squared. X squared plus 4x plus 2. Okay? Then we have to write this one as a over x, b over x plus 1, c over x plus 1 squared. Alright? Again, we have to look at the form when you combine this one using common denominator. So I need here, our common denominator has to be x times x plus 1 squared. So x plus 1 squared, x plus 1 squared. So your numerator from that would be this. X times x plus 1 squared. I need x times x plus 1, x times x plus 1. Over here I need x over x, right? Cx. So, what we have here is numerator x squared plus 4x plus 2 is equal to a times x plus 1 squared, b times x plus 1, c times x. Okay? So, yes, just like before, we can plug in x equals 0 or x equals negative 1. Let's plug in x equals 0. 0, 2 equals a, 0, 0. So, a equals 2. Alright? Now, secondly, when x equals negative 1, negative 1, 1, negative 4, 2. 1, negative 4, 2. So negative 1, and then negative 1 is 0, 0, negative 1 c. So this is negative 1. So C equals 1. Alright? So you can get A and C are really easily. How about B? Now if you have all different linear factors, there should be a third value, but this one was repeated, so either -1 and 0 will both get rid of B term. So we don't have anything about B. Well, that's okay. This is identity, which means it is true for all x value. Let's choose the next simplest one, like 1 or 2. Okay? 1. What do you get? 1 plus 4 plus 2. So 7. We already know that A equals 2. Plug in 1. 1, 2 squared equals 4. Right? 1, 2. So 2b. Then the C equals 1. X equals 1. So what do you get? 2b. So 7 equals 2b plus 8, 9. 2b equals -2, b equals -1. Okay? So when you have some repetition, that's okay. Still plugging in 0 of the denominators and then other simple values and solve for the rest of the coefficients. Okay? So your integral is a equals 2. 2 over x plus 1. Here, b equals -1 over x plus 1, and this is x, sorry about that, and c equals 1. 1 over x plus 1 squared dx. Obviously, this is 2 ln of absolute value of x minus ln of x plus 1. Look at this. X plus 1, -2 power. Adding 1, -1, so negative x plus 1 to the negative first power. Or 1 over x plus 1. Okay? Okay? All right. Now before we go further, I want to do some review. Tangent inverse of x derivative was 1 over 1 plus x squared, right? And tangent 1 over x, x over x. So 1 over a times tangent inverse of x over a. Let's take the derivative and see what happens. Constant 1 over a out. Tangent, it's a chain rule. Derivative of outside function, tangent inverse function's derivative is 1 over 1 plus whatever the inside square, right? Times derivative inside, 1 over a times x, derivative is 1 over a. You have a squared times this in the denominator, which is 1 over a squared plus x squared. All right? Therefore, integral of this one (1 over a squared plus x squared) integral is 1 over a tangent inverse of x over a plus c. This is what I want to derive. Okay? Okay, using this, let's do the next problem. But before we do that, let me check video recording. All right, let's do the next example, which is 6. 7. We already did 7, right? So 8. Example 8. Evaluate x squared plus x minus 9 over x cubed plus 9 of x dx. Again, I'm going to call it I. Integral I. So, first of all, again, rational function whose numerator has a smaller degree than the denominators. So, this standard form. Then you have to factor denominator, like this. Okay? So you can see, this is irreducible polynomial, square plus square. Or if you set it 0, you get imaginary 0, irreducible quadratic. So you have to have a over x plus. Now, when you have a irreducible quadratic, the way we find A, B, C, these coefficients probably will be easier using the second method. I mentioned in the example, I believe 6, the very first example of integration by integration using partial fraction, which is just comparing coefficients. What I mean by is that a times x using common denominator, you have this, right? So you have x squared plus x minus 9 equals a plus b x squared, a linear term cx, and then constant term 9. And then we compare these to be identical. That means this has to be 1, this has to be 1, this has to be negative 9. From there, a must be negative 1. Well, c equals 1. Negative 1 plus b equals 1, so b must be 2. Alright? So normally it's easier to use this second approach, comparing coefficients, rather than plugging in some x values. Alright? So your integral I will be integral of a equals negative 1 minus 1 over x and b 2x plus 1 over x squared plus 9. Now, you've got to be careful here. This one, you want to split 2x over x squared plus 1 and 1 over x squared plus 9, which is 3 squared dx. Then 1 over x integral is ln of absolute value of x. What about this one? If I call this is u equals x squared plus 1, du equals 2x dx. So this is 1 over u du. So ln of absolute value of u, which is absolute value of x squared plus 1. Alright? This is a simple substitution. The last one, we just learned it. 1 over x squared plus a squared integral is 1 over a tangent inverse of x over a. A equals 3. So this will be 1 over 3 tangent inverse function x over 3. Okay? So when you have this kind of thing, you split this way and use this one as, substitution. And this one is just tangent inverse of x over a. Now that was easy because you didn't have linear term in the denominator. What if you do? Then it's not going to be this easy. Alright? So let's consider that case, just for that. Let's say in the process of this, let's say you are dealing with something like this. this you could consider this is some intermediate step of the entire problem of partial fraction. So you end up getting this x squared plus 2x plus 5dx. This is irreducible. When you set this one equals 0, you get imaginary number. So you have a linear term, unlike this. So you cannot use this kind of thing directly until you do. Look at this. You can do completion of square. 1 and 4. You can do different ways, but in the end you can have x plus 1 squared plus 4, 2 squared over x plus 2 dx. And then we use u equals x plus 1. Then du equals dx, x equals u minus 1. X equals u minus 1. U minus 1 plus 2, okay. U squared plus 2 squared du. So it's plus 4. Now you have this form, right? You have this kind of thing. So, if you have a linear term in the irreducible quadratic, you just do completion of square. Then you do u over u squared plus 4, 1 over u squared plus 2 squared du. Now, this is, let's say, v. 2u du is 2u du equals dv, right? So it's 1/2 of ln of this one, right? Just like before. Okay, and this one, as we learned, tangent inverse u over 2. Okay, and going back to x plus 1. X plus 1 squared plus 4. And the inverse x plus 1 over 2. Okay? This is how we handle when the denominator has linear. Just completion of square. Now what if, final case, we only consider this, and I mentioned that even for this we can handle easily by using long division first, right? For that case, just do long division or whatever, just divide, okay? And set where p of x equals some q of x plus remaining there. Then p of x over q of x, lower q of x polynomial, r of x over, when you do long division, or however you do it, obvious degree r is less than degree q. So we do use partial fraction there. And this is a polynomial, so you can integrate easily. Alright? That's the case we are considering. So example 10. Let's do it here. Example 10. So evaluate example 10. Evaluate this one, x to the 4th over dx. Okay? All right, first of all, we have to do this long division. X to the 4th minus x to the 3rd, 10x squared minus 8x minus 9 divided by x to the 3rd. it's better to write it as filling up the missing terms. We need to get rid of this. So x times that, x to the fourth, 0, and minus x squared, 0. Subtract, 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 subtract. And again, this one, negative 1. Negative 1 times this, 0, negative 9x, 0, subtract x squared plus x minus 9. So, that means if you do this division, then what? So this one will be quotient minus remainder over divisor, right? So your integral will be this. If I call this integral, so I. All right. Quotient plus remainder over, and this one is 1/2 of x squared minus x plus. Now for this one, you have to do partial fraction. Now that your numerator has lower degree. Well, we already learned this one. This is from example 8. Right? Example 8, that was minus ln of absolute value of x plus ln of x squared plus 9, 1/3, tangent inverse of x over 3 plus c. This is from example 8 results. Okay? So it covers most of the cases. Okay? In this course, we don't deal with higher power of irreducible quadratic polynomial. That requires more techniques. But rest of the case are settled here. So most of the rational functions from now on, you can actually integrate using partial fraction techniques. Okay, that's the end of the second part of combined sections, section 5.7 and Appendix G. And that's the end of the second part of the 2 parts. Okay, the end of the combined section. Thank you.